Okay, so students will get started and we will continue our discussions uh, with what we left in the previous class. So I hope my screen is visible. Students, is my screen visible? Okay, fine, thank you. So questions can be asked anything as such, where y is equal to a into b plus c, or I can even ask a into b plus c plus d plus e. Okay. Now I will tell you one trick. Okay. Now just count how many parameters are here: a, b, c, d. Okay. So which means you should have two times the number of transistor. Okay. So I have a, b, c, d, which means about four different parameters, right? So into 2 twice, so 8 transistors, 1 2 3 4 5 6 7 8, just a form of cross verification. Okay. Now the most important thing that will have to always keep in mind is this rule. Okay, this rule to be always kept in mind. So with this we actually finish our CMOS implementation. Next, with regards to logic gates, okay, we have seen the Boolean algebra, we have seen how CMOS switches are implemented, we have seen the logic gates and the truth tables, right? So these are some of the things which we already saw in our initial classes. The symbol for AND gate, OR gate, NOT gate. Okay, buffer is nothing but the same. You don't have a bubble there. Some authors do represent, the buffer in this format. Whatever is your input, the same thing is your output. But in NOT gate, it is just the reverse, right? 0, 1, 1, 0. So it is just the reverse. And in OR gate, as you all know, addition happens, and in AND gate, multiplication happens. I think all of you are very familiar with these basic concepts. Then we have seen the NAND gate, multiplication with the negation, right? And the NOR gate, XOR gate. Okay. One speciality of XOR gate. Can someone tell me what XOR gate is? A special gate? Why?
All gates can be realized using that gate.
Uh, Come again, please.
All other gates can be realized using XOR gate.
Yes, that can also be done, but there is one special application for XOR. Actually, what you're telling is for NAND and NOR. Okay, for NAND and NOR, these are universal gates. Anything can be implemented. XOR is a special purpose gate.
Sir, is it because like the even number of one input should give an output of zero?
Not only once, it's even for zeros. Okay, so same number of inputs. Okay, if the inputs are same, 0 0 is same, I get 0 as my output. If 1 1 both are same, right, I'm getting 0. If it is different, 0 1 or 1 0, I get 1. So what is it acting like? It is acting like a comparator, right? It will tell me if two bits are same or two bits are different, isn't it? So if I have same bits, output is 0. If I have different bits, output is 1. So this is the specialty of XOR gate. I can use it as a comparator in some of the circuits, right? Okay. Next is your XNOR. Okay, just the reverse of your XOR. Okay, this is how I think you have seen all this in your basic electronics. Fine. Uh, You don't have to know of these definitions. Fan in is number of inputs to a gate. Fan out, I think I have explained this. Fan in and fan out, the number of branches that comes in and the number of branches that comes out, right, in the initial classes, where it is, the number of loads the gate drives, which means how many inputs it has is your fan in, and how many outputs, how many it drives. So that is your fan out, branch out and branch in. So if I have to implement using a equation, okay, a into b, have you done this kind of implementations in your basic electronics? I give an equation and then you use your basic gates and implement. Have you all done this? Yes, fine, thank you, Surya. So you have a into b bar, okay, this tick represents your bar, okay, plus cd. So a into b, this is nothing but my NAND operation. AB is here, I use a NAND gate. CD multiplication, so I use an AND gate, and the both of the terms are to be added. So I use a OR gate, I get my final function, right? Similarly, I put another function here, okay. A plus b bar, I use NOR gate, and then I use an AND gate because it's been multiplied. Fine. We will be seeing this extensively in the next module actually. This is a kind of intro to your second module, okay, which is all about your analysis and design of combinational logic. We will be seeing extensively based on these adders, okay, full adder, half adder. So this is one such example, okay, where you have uh, 3 bit, so it becomes 3 zeros to 3 1s, okay, and your sum and carry out. I think adder, have you all gone through adder, basic electronics? Full adder, half adder, have you gone through these concepts? Have you come across? Yes, fine. So it becomes easy for us. So zeros, I have sum and carry 0, 0 1, when I add I get sum 1 but carry is still 0, okay. 1 0, the same result. 1 1, okay, it becomes 0 but carry 1, okay. And similarly with 1 0, the same case. 1 1, the same case. 1 plus 1 is 0 and then carry 1, okay. 1 1 0 1, triple 1, okay. So here 0, 1 plus 1 is 0, 0 plus 1 is 1, and carry is also 1. Carry is also generated, okay. So if you take the equation, okay, it is just like AB, okay, A bar B bar C in plus A bar B C in plus A B bar C in plus A B C in. So this will be your equation for your sum. So this is nothing but your XOR, right? A XOR B XOR C. Next your sum and carry, it is just like A B B C C, right? Okay. So this is your general block diagram of adder. A B C are your inputs, sum and carry or C out is your output. The next thing that we have to see here is the pass transistor. Now, as I told you, transistor will also act as a switch, right? So when I say it acts as a switch, when can someone tell me NMOS turns on if I give a 0 or a 1? Correct. It's 1. Correct. Now, how about PMOS? How can I turn it on if I give 1 or 0? Correct. It's a 0. Thank you, students. Now, since we know these concepts basically, okay, so it becomes very easy for us to understand what is a pass transistor. As the name suggests, pass transistor is nothing but it is just passing a value, okay. It is just passing a value. It is not doing any manipulation to any data, but then its function is to only pass value. Now just look at the information that I have on my notes here, okay. Now this is telling us that for what voltage which one is turning on. So this is going to be a recap of what we studied actually in the previous lecture, right? So I have a zero value here, 0 volt, okay, and then I have 5 volts here. So 0 is low and 5 is high. Okay, so I can even take 12 volts or 15 volts. For simplicity, we will take 0 and 5. In simple, I can even call it as 0 as low and 1 as high. Okay, so 0 and 5. So ultimately, it is low value and high value. So if I pass through an NMOS, if I pass through an NMOS, I will actually get a degraded 1. I will actually get a degraded 1. The reason why I get a degraded 1, what is a degraded 1? If I pass 1 as my input, at my output also I should get 1, but instead I will get 1 minus VTN. Okay, VTN can be about zero point 0.7. Okay, now this zero point 0.7 is nothing but your threshold voltage. VT is nothing but your threshold voltage. I think you would have studied about threshold voltage. Can someone unmute and answer me what is a threshold voltage? Lavanya, what is a threshold voltage? Lavanya,
Yes, sir.
yes, what's the threshold voltage?
Uh, the threshold voltage is the voltage required to create like a path between the gate and the
Exactly, so that is a channel, right?
a channel.
Thank you, Lavanya. So when I give a potential, okay, about zero point 0.7, so that is going to help me out in creating a channel between the source and the drain. Okay, so this path gets connected between the source and the drain. Maybe in my next lecture what I will do is I will show you guys a cross-sectional view of an NMOS and a PMOS, a colorful cross-section, wherein we will be able to understand as to how a channel is formed. Of course that is not needed for your syllabus point of view, but I will just explain those so it will be easy for you to understand. Okay, right. So if I have a low value 0 and a high value 5 here, so my output is going to be a degraded 1. Why is it going to be a degraded 1? Because it needs to turn on, because 1 is used to turn on the NMOS, right? So a part of 1, it is just like, I give you some food. Okay, I say I have given you say 5 rupees. Okay, let's take it in numbers. I have given you 5 rupees, and you have to survive for the day. Okay, so what you will do is probably you might use 3 rupees for your food. Just an example, 3 rupees for your food, and the remaining 2 rupees is going to be in your pocket. So this is just the same. Okay, so your NMOS is actually using your voltage which you have given at the input side to turn on itself. So once it turns on itself, then the remaining part is going to come out as output, right? So that is what you have to understand. So with NMOS, what is going to happen? I'm going to get a degraded 1. Okay, next with PMOS the reverse happens. Okay, instead of getting a proper 0, I am going to get a degraded 0. Instead of 0, probably I might get say 0 0.1 or 0 0.2, something like that. Okay, a little higher level. Can you see this dotted line here? It should have been here, but then actually the bold line is the practical value. Okay, so similarly here in your NMOS, the bold line is your practical value, but it should have been in the dotted line. So this difference that we see creates a degraded value, degraded 1 for NMOS and degraded 0 for PMOS. Okay. So in order to get these um, errors rectified, what we do is we connect both together. So I connect my PMOS here. Let me annotate so it becomes easy for you to understand. So if you can see, this half is your PMOS, okay, and this half is your NMOS. So just that it is rotated and connected. That's it. Okay. So both are just rotated. It is just flipped and connected. So I have a PMOS as well as I have a NMOS. So with this, what is going to happen when I give a 0? Okay, instead of having a degraded 0, okay, that will pass through my NMOS. Instead, it will pass through my NMOS. And when I give a high value, instead of passing through NMOS, I will pass through PMOS. So instead, I will not get a degraded 1, I will not get a degraded 0. So I will get a proper 0 and I will get a proper 1. Now this is the reason why we connect PMOS to VDD and we make PMOS to actually pass the high value. Okay, and NMOS is connected to ground and we make it pass the low value. If we do the reverse, okay, if we make NMOS to pass the high value, I don't get proper high. Instead of 5, I might get about 4.3 because it is 5 minus 0.7, right? So I'm not getting a proper value. Similarly here, the same case happens with my PMOS. Okay, so how do we solve this problem? I combine both NMOS and PMOS and then I give my values. Higher values, which means 5 volts is passed through your PMOS and lower values is passed through NMOS. Now recall back to our general structure. Recall back to our general structure. This is why we connect NMOS to ground, because we want a good 0, and we connect uh, PMOS to VDD, which means I wanted to pass a proper or good 1. But if we reverse this too, if I put PMOS here and if I put NMOS here, even VDD is going to get degraded and the ground is also getting degraded. So which means my communication is not happening properly, right? So there is going to be a breakage in voltage. Okay, there is going to be a degraded value, which is actually not advisable in the field of communication and circuitry. Okay, so this is about your pass transistor. Now there is a textbook called Neil West, okay, um, in which he talks exclusively about pass transistors. Okay, I have underlined few things and this is going to be helpful, okay, for you while writing the answer. Okay, uh, an NMOS transistor is almost perfect switch when passing the 0. That is what we discussed now, and thus we say it passes a strong 0. Okay, and then NMOS transistor is imperfect at passing 1. Okay, which means it actually passes a degraded 1. So we call it as a weak 1. So what do we do? By combining NMOS and PMOS in parallel. Okay, so what do we get? We get a combination called pass transistor. Pass transistor. Okay, so this is the same representation. Either you can use these diagrams to explain your answer, or you can use these diagrams to explain your answer. Anything is fine. I will accept both of these answers. Okay, so I have my source, gate, drain here. This is my NMOS and this is my PMOS, source, gate and drain. Is it visible, students, or do you want me to zoom in? Is it visible? You want me to still zoom in? Okay, is this level comfortable? Okay, thank you. So we have a source here. Okay, source gate. Okay, so we are looking at NMOS, source, gate and drain. Source, gate and drain. This is a PMOS. I have a bubble here, so it's a PMOS. I don't have a bubble here. It's an NMOS. Okay, when my G is equal to 0. Okay, when my gate is 0, as I've told you, NMOS will turn on only if I give a 1, right? So gate is 0, so there is no connection between source and drain, so which means the switch is open. Okay, and at my input, if I give a when G is equal to 1, I get my output. Okay, but when G is equal to 0, okay, when I pass a 0, okay, then I get a strong 0 using my NMOS. Now let us take the other case here. G is equal to 1, the gate is connected, and then I try to pass 1. Okay, so I am passing 1 to an NMOS. So what is going to happen? It is going to give me a degraded value. Why is this degraded value? Because of my threshold voltage. What is this threshold voltage? The minimum voltage required to turn on the transistor. So if you're using a silicon, it's going to be about 0.7, and if you're going to use a germanium, it's going to be about zero point 0.3. These are standard values, theoretical values. Practically it could change, or it can probably come down, or a little higher. So instead of zero point 0.7, it can be about 0.75 or zero point 0.8, or it can come down to 0.65, or 0.68 or something at that level. Okay, so with respect to PMOS as well, you will have source, gate and drain. And remember, what's the fourth terminal? It is the substrate. Substrate is connected to source, so we just represent three terminals here: source, gate and the drain. So when G is equal to 0, okay, when I pass a low value, the switch is connected, which means the transistor is on. So when I say the transistor is on, when I give a 0, it's a degraded 0. But when I give a 1, okay, and I try to pass the values, okay, it's going to, when G is equal to 0, okay, then what is going to happen? It will actually give me a strong 1 at your input. If there is a 1, this is your source, gate, drain. So at your source, if it is a 0, it's a degraded 0. At your source, if it is a 1 and your gate is 0, which means the transistor is in operating condition, and I'm passing one value. So if I pass a one value, which means I'm passing a high value. High value can be VDD. VDD can be 5 volts. Okay, so I'm passing a high value here, so it gives me a strong one, which means a proper VDD. So what do we conclude by these discussions, students? I want someone to unmute and respond. What do we conclude with these discussions? Supriya, can you tell what we can conclude from the discussions that we did so far? Supriya, can you tell us what we can conclude with the discussions we did so far? Someone else would like to do that? Someone would like to summarize? Someone would like to summarize as to what were the discussions done so far? Swati, can you do that? Swati K. Swati M. Someone can unmute and respond. Anyone? Just summarize what we learned so far. Rohit, would you like to answer? Yes, go ahead, Rohit.
Like this topic said that
Ah,
you provide an input of one in NMOS, you obtain a degraded output of one. So
okay.
the gate is 0. And in PMOS, you provided a 0, you obtain a degraded 0 in the output.
Yes, yes,
But when the gate is closed in NMOS, you obtain a
exactly. Right. Thank you. Thank you, Rohit. Okay. So the thing that we have to understand here is if we are using an NMOS, okay, we should pass 0. Okay. And if we are using a PMOS, we should pass 1. So that will give us proper values. So this is what we can summarize from the discussions done so far. Okay. Now this is a transmission gate. You don't have to remember this. Okay. You will have to use only this diagram. Okay. Either this diagram you can draw in your test and exams, or you can use the previous one which I showed. Yeah, this one. Anything should be fine. I will take up any of those. Okay. So I think with this we actually conclude our module 1, which is principles of combinational logic. Okay, where we had discussed a lot of concepts based on map, MEVs, transistors, NMOS, PMOS, CMOS, De Morgan's theorem, canonical forms, generation of switching equations, the K maps we have seen exclusively with 3, 4, and 5 variables. Then we have even looked at don't care terms, right? Then map entered variables, uh, which is 3 and 4 variables, right? Then realizing functions using MOS logic. One thing that I want to stress here is let's go back to incompletely specified functions, which is don't care functions. Okay, I think we had kept it on hold, and we will just try and finish that in this class quickly. Uh, so that it becomes easy for us to continue in the next class with a new module. Okay, maybe all of you are clear, right? You have to remember these rules. Okay, these rules are important. So once you know these rules, you can actually apply them and get a simplified version.
so will you send the notes to the same?
Yes, yes, I will. Okay, I will do it. Right. So we have seen this POS, right? Don't care conditions. So in some cases, okay, what will happen is we can use a don't care. Okay, of course you guys know it, but just I want to recall, I want to close this module with the don't care conditions. Let's take a function f w x y z and summation 137 11 15 and don't care terms. Remember we used to write plus d. Okay, uh, let me show you. We used to have plus d here, right? So the same fashion we are using it here. Okay, so this is kind of going to be a recap for you. Okay, so don't care terms will be wxyz, okay, is equal to summation 0 to 5. So I'm using these don't care terms. So I try to enter the data. Okay, so for simplicity I will use my I will value my squares. Okay, I've written 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I will value my squares, and wherever I have these 1, 3, 7, 11, 15. Okay, 1, 2, 3, 4, 5. So 5 ones. So 1, 2, 3, 4, 5. 5 ones, and then I will be using the don't care terms 1, 2, 3. So don't care terms is at 0, it's at 2, and it's at 5. Now the best thing about don't care is that you can use them for grouping. Okay, let's take this as an example. I just have two ones, so I want to have a group of 4. So I have a don't care here and a don't care here. So I can take this whole thing as a group and make it just one group. How are we getting w bar z? Okay, how are we getting it? You should actually look into this function. Okay, the row and the column. Okay, yeah, I guess it should be w bar x bar. This one should be, yeah, w bar x bar. Okay, then you will have another function here. Okay, where you will get w bar z, and here you will get y z, y z. Okay, because 0 0 0 1 1 0 1 1, all this will get cancelled out, and you get y z. So this is how you get your final equations. I have written the explanation here where you know if even if you don't take these don't care terms, you just take this group and only this group, and since these two ones are already covered, I don't have to take another equation here. Right, you're able to get me what I'm saying. These two ones are already covered in this group. Okay, this is group 1, and in this group 2 I will cover these ones. So if I see there is just two don't cares here, so I can just leave it because these ones are already covered and I have a group of 4 ones, right? So that is what I have mentioned here. Another combination that we can think of is you know 2 4 5 13 14 plus don't care 0 1 8 10. Okay, so as usual I'll be filling in those values, grouping them. The only technique that you have to remember here is grouping. Okay, so I have two ones here, I will group them using these two don't cares. I can get 4 ones, so I will use them, and then I have just one single one here. So instead of single one, what I will do, I will group them with group it with another don't care, and then I just have single one here. Instead of single one, I will use this don't care and make it another group, right? So this is how I will get my final equation. So ultimately the higher the group, the better. Okay, so you can see it here, exactly the same thing that I have done. Okay, now another technique, right? I have used here another technique. So I will use these corners. Okay, these corners also I will use, and I'm going to get one group, these 4 ones, and then these 2 ones and 2 ones, right? So simplified expression depends on how perfect you do your grouping. Okay, so this is about your don't care terms. Fine. Right. Okay, so what we'll do now is we will just start off with the second module. Okay, are you all able to see my screen? Yes. Student, you're able to see my screen? I have written module 2. Yeah. Okay, fine, sir. Thank you. So we will just try and understand, okay, as to what exactly is in this module. So here it is about your analysis and design of combinational logic. We will be studying about multiplexers, then decoders, encoders, and about adders, uh, code converters. Okay, so these will be our major uh, points of discussion. right? So anyway, you can actually go through this one by one. The synthesis of combinational logic starts with a problem statement and progresses a series of steps. Now, as you saw your minimization techniques, okay, we will have a problem. The flow chart, okay, the flow chart you should remember a problem statement, and then we generate truth table, right? So once the truth table is generated, we try to have a simplified, we have an equation, then we have a simplified equation, then we get a final circuit which is actually optimized. So that is what is mentioned here, okay, which is nothing but the synthesis of combinational logic starts with a problem statement. So we will have a problem statement. We even saw a problem, right, where it was two operators and how the motor moved from one point to another point, right? We solved a problem also based on problem statement. Terminating the final circuit design. So circuit design is going to be your final step. The combinational logic design steps are these. Okay, so these 6 steps. Okay, these 6 steps are going to be your steps to be followed for designing a combinational logic. Okay. First, we develop a statement describing the problem. Then we construct a truth table based on the problem. Okay. So if I ask you what is a truth table, it's nothing but a relationship between input and output variables. Isn't it, students? Don't you think truth table is a relationship between input and output? Yes or no? Yes. Do you think a truth table? Don't you think truth table is a relationship between input and output? Yes. Thank you. Next, the third step is nothing but we use key maps, or of course, for your syllabus point of view, we are not using Quinn McCluskey. That's another different method, just like K map and MEV. MEV is map entered variable. So we also use another technique called Quinn McCluskey to simplify functions, and we get a simplified version, and we put them in standard SOP and POS form, and we get a simplified equation, and thereby a simple optimized circuit. So this is all arranged. Okay, we arrange the simplified equations to suit logic primitive type, and what we do is, if if needed, we use NAND and NOR, or we just use the basic gates and or inverter. All these basic gates we use, or as per the problem statement, we can also realize using our universal gates, which is NAND and NOR. Then we draw the final logic diagram and the document the design. Okay, documenting the design by identifying variables, then indicating the levels if possible, and we provide a truth table. So this is a complete step as to how a combinational circuit is designed. Right? Okay. Now we will just see this for our discussion. Okay. So we will just understand the problem statement and how the truth table is written. Okay, how the truth table is written. So these 2 points we will concentrate. So the problem statement is design a combinational circuit that will multiply two-bit binary values. So we need to design a circuit which will actually multiply two-bit binary values. Now how do we go about doing this? So since it's a two-bit, okay, we will have 4 input variables, and I will name them as a1 a0, b1 b1 b0. So this becomes my two is one is a and one is b, 2 bit, and each variable is 2 bits. So a1 a0, b1 b0. Are you all understanding, students? I'm just trying to decode the problem. You're able to follow what I'm trying to explain? Yes. Thank you. And we will have 4 output variables, okay, because we have a1 a0 and b1 b0. We will have 4 output variables. So what are those? P0, p1, p2, p3. okay, are needed. The four output variables are necessary because maximum product of two-bit values. Okay, suppose let us take 3 into 3 gives me 9. Okay, so to represent 9, can I represent it using 3 bits? No, maximum, even if I put triple one, okay, that's not going to happen. So I will have to use another bit, okay, another bit which is nothing but the fourth bit. So which means I will need 4 bits as my output variable, okay. And meanwhile we construct our truth table, okay. A1 A0, B1 B0, 4 inputs. So from 4 zeros to 4 ones, a normal combination of binary numbers. Okay, 4 zeros to 4 ones, normal combination. Now here what we have to do is we have to multiply. Okay, what is the question? Design a combinational circuit that will multiply two 2-bit binary values. So we have to multiply here. Okay, so I think what we will do here is we will try and understand up till here the first step as to how many input variables we are going to have and how many output variables we are going to have, and how the truth table is getting constructed. So I'm going to multiply this 0 into 0. So it is going to give me 0. Okay. 0 into 1. This whole thing I take it as 0 and this one I take it as 1. So 0 into 1 is what? 0. So I write all the bits as 0. Let us take some case where I have 1 and 1. So in this case, look at this case. Let me just annotate. It will be easy for you to understand. Okay, so I am considering this case. Okay, this case I am considering. So here what you should do is you should have a separation. Okay, this is a separation. So this is my 1 bit. Okay, this is my 1 bit. This whole thing is my 1 bit, and this b1 b0 is another variable. Okay, so totally I take this as a. This whole thing is taken as a, and this whole thing is taken as b. Now again b will have b1 and b0, a will have a1 and a0. So I think that part is clear. So I am multiplying a and b here. So a is 1, okay, a is 1 and b is what? 1. So 1 into 1 is what? 1. So I am giving 1 here. So have you all followed as to how we are developing the truth table, how we are multiplying these bits, students? Is it clear?
No, sir. Could you explain that again?
Once again, okay. Now 0 1, don't take it like a 4 bit now. That's why I have drawn a line. Okay, so this is like 2 bits now, 2 bits and 2 bits. Now remember, what is our question? Multiplying two 2-bit variables, right? So I am now it is just a 2 bit for me. 0 1 is 2 bits, 0 1 is again 2 bits. So I have to multiply 0 1 with 0 1. So 1 into 1. Okay, what is it? 1 into 1? 1 into 1 is 1. So how do I represent 1 here? This is the only way that I can represent 1, right? If I put 1 here and 0 here, what will it happen? It will happen 2, right? 8 4 2 1, isn't it? So the same concept. So similarly you can try to analyze for the other values as well. So students, what we will do here is we will stop. Okay, we will stop till this truth table, and we will follow it up okay, in the next class. So what I will do here is I will share. Okay, so we will continue in the next class, and we will see the remaining things, how we can actually get it done. Okay, we will solve this problem.